In Chapter 2, we're going to be discussing geometries, intermolecular interactions, and physical properties. In this first part of Chapter 2, we're specifically going to be looking at the geometries associated with molecules. So first to review VSEPR theory. In VSEPR theory, this is valence shell electron pair repulsion theory. And what it does for us is it really helps define the shape that we have of our molecules. It tells us that the electrons are always found in groups around this central atom, and that those groups are going to repel each other. They're all negative because of the electrons, and those negative charges repel, and it's this repelling factor that actually determines or dictates the shape that we have for our molecules. We have two types of geometries that we're going to be looking at. The first is going to be our electron geometries, and these are going to describe the orientation of all the groups around the central atom. So every single group of electrons that we have, we're going to define the shape associated with it. For molecular geometries, it's going to describe the arrangement of just the atoms around the central atom. So this is oftentimes referred to as the shape that a molecule has when we look at the molecular geometry. In organic chemistry, what we're going to see is that our structures are going to be very, very large. So we're actually going to have more than one central atom that we're going to be looking at or defining geometries or shapes for as we look at this very large structure. So we'll have a bunch of molecular geometries that we'll define to give us the overall shape of this molecule. So we're going to be talking about all the geometries associated around the central atom, reviewing the information from your freshman course. So the way this table is set up is we're going to be looking at the number of electrons that we have around the central atom, which defines then our electron geometry. We'll be talking a little bit about the angles that we have between those groups of electrons, the number of lone pairs that we have around the central atom, which also then defines the number of atoms that we have around that central atom, and then that molecular geometry, or remember this is the shape that we would then have around our central atom or for the molecule as well. So the first one is going to be our two electron domains around the central atom. So for my kit here, we have our central atom, and then we have our electron domains. So from here, this is a nice linear shape. You can see that we have a nice 180 degrees between those two electron domains. So this is really what defines as linear. If both of these have bonds on them, so both of these are what we would refer to as bonding electron domains, we also have a nice linear molecular geometry or shape as well. For the next one, we have our three electron domains around our central atom here in the middle. With those three, you can see it's what we refer to as a trigonoplanar shape. So it's a nice flat shape. If I turn it sideways, you can hopefully see that it is a nice flat shape. So this is referred to as trigonoplanar. There's 120 degrees between every single one of those electron domains. If they are all three bonding electron domains, so if I have atoms on all three, we still have a nice trigonoplanar shape as well. If in this trigonoplanar shape I have one lone pair, the way I'm going to denote a lone pair on my model kit is this nice little red sphere up here. That's what's going to denote a lone pair. So if I have one lone pair, that means I only have two atoms attached. So with those two atoms, I see this nice bent shape. So remember, when we define shape, we're going to ignore anything that is not an atom. So we're only going to focus on the atoms for our shape. So we see that we have this nice bent shape. It does not become linear, even though there are only two atoms attached, because we do have electrons that are still repelling those atoms away from each other. So we do have a bent shape that would have about 120 degrees between those two atoms. So this is our trigonoplanar electron domain geometry, where when we have one lone pair of electrons, it does become a bent shape for us. The fourth geometry that we want to worry about is going to be our tetrahedral geometry, where we have four electron domains. It is definitely not a flat shape. It's our tetrahedral electron domain geometry. Between all of these electron domains, it's very symmetric, and we have 109.5 degrees between all of them. If all of these are bonding electron domains, we have a nice tetrahedral shape as well. This is going to be one of the ones that we will focus on most often with organic chemistry, because carbon can form four bonds. So we do really see a lot of this tetrahedral shape when we look at our organic structures. If in our central atom we have one lone pair, so there's my lone pair, we have three then atoms attached to our central atom, our shape now becomes trigonal pyramidal. So you'll notice it does not become planar. Hopefully you can see that there's a little pyramid there. If I try and set it on my hand, there's a pyramid. We have a top point and we have a base of 3. So this is what we refer to as a trigonal pyramidal shape or molecular geometry when we have one lone pair. If we have two lone pairs, it goes back to being a nice bent shape. So here are my two lone pairs. And if I cover them up and ignore them, you'll see that we once again have a nice bent shape. This time the bond angle there would be about 109.5 though. So you'll see a difference between the two just in terms of the bond angle, but they're both classified as a bent shape or bent molecular geometry. So with our VSEPR theory, we do have these angles that you do want to know for me, and you want to memorize or know what those ideal bond angles are for each of those electron geometries. But what we are going to see is there is some angle strain that is associated with a lot of the molecules that we're going to be looking at. And angle strain comes because our molecules, they're going to deviate from those ideal bond angles under certain conditions. It's called a strain because this deviation from ideal is going to cause an increase in the molecule energy. So the farther that we deviate from ideal, typically the higher the angle strain, the higher the energy associated with the molecule. We are going to see angle strain anytime we have a cyclic compound. So anytime we try to connect all of our atoms in a cycle, we've seen a few of those already with resonance and with our epoxide, that causes some angle strain. We're going to deviate from those ideal angles, and it causes a strain, it causes an increased energy with those cyclic compounds. We're also going to see it because of lone pairs. So if we go back to our trigonal planar, and then we go back to our bent structure, this lone pair is going to take up more space, so this bond angle is going to deviate. It's actually going to be smaller than 120. So you want to recognize that these lone pairs are going to make any of our bond angles deviate slightly from that ideal, and it will force them to be smaller than what the ideal angle is. Multiple bonds are also going to do the same thing. So if we throw in any double bonds, any triple bonds, we're going to see a deviation as well. So if in this structure, for my trigonal planar, I view that I have a double bond here, where instead of a lone pair, if we think of this as a double bond, it is also going to compress these two together. Double bonds have more electrons in them, so they have a higher repelling factor associated with them. So it's going to cause any single bonds within the structure to be closer together. The bond angle between the multiple bond and the single bond, this bond angle would become much larger than what the ideal one is as well. So multiple bonds are going to cause some deviations and therefore give us a little bit higher increase in energy associated with the molecule as well. So now let's put this into the context of our organic molecules and what that's going to do to the way that we draw them and the way that they look as well. So first off, I want to talk about alkanes. Please remember that for our alkanes, this is where we have carbon-carbon single bonds within our structure. When we look at these carbon-carbon single bonds, we're going to be drawing them, if you're practicing your shorthand notation, we're going to be drawing them in these V-type patterns. Those V-type patterns are really due to the tetrahedral nature that we see in each one of our carbon atoms. So each one of these carbon atoms is going to have that tetrahedral shape. So if we draw this out in our Lewis structure format, what we're going to see is that three-dimensional form that we can put in as well. So I've drawn in some new line notations that you are going to want to be familiar with, called our wedged and our dashed lines. So these lines here that I have darkened in and kind of made a little bit of a triangle, these are what we refer to as a wedge line. Those wedge lines means that they're pointing out at you. So you want to think of those lines that hydrogen is coming out of the plane of the screen and is pointing out at you. You could reach out and you could grab it. The other line that I have drawn here is what we refer to as a dashed line. And that is going to be going back behind the plane of the screen. So you want to think about it behind your computer screen. It's going away from you. So it gives us that three-dimensionality that we see with that tetrahedral shape. So because of that, when I connect my three atoms together in that tetrahedral shape, we automatically draw these what I call V's. So you want to start being very, very particular with how those V's are drawn. You'll notice within these V's, there's nothing there. So what I want to be very, very careful about is when we are drawing our zigzag pattern, it is this zigzag type pattern if we have very long chains. I'm never going to draw anything down here within this V. You'll notice that any of my hydrogens are going to be pointing straight up. They're in that dashed and wedged line. So if you can look at the model with the 3D kit, you'll see that there's nothing in here. There would be nothing in this area. You never want to draw anything in these V areas. And this is going back to that tetrahedral shape that we have associated with our carbon atoms when we're dealing with those alkanes. So if you can kind of look at the model kit, here's the hydrogens that are pointing out at you. There's one over here pointing out at you. There's one up here pointing out at you. And then we've got ones that are going back behind the plane of the screen as well. And the regular lines that we have drawn are the ones that we would say are in the plane of the screen. And we see these nice little V's, this zigzag pattern that we have associated with our alkanes. The next one we're going to talk about is our alkenes. Remember with alkenes are those double bonds. So this would be our double bonding pattern that we would have anytime we talk about an alkene. With an alkene, we're still going to see that same type of zigzag pattern because the shape associated with those carbon atoms is going to be our trigonal planar shape. So remember, it is going to be our trigonal planar shape. We have 3 electron areas around it. One of them just happens to be that double bond. So we are going to see that same type of V pattern associated with our structure. What is going to change when we get ready to draw this, if we were to look at our Lewis structure, I still have my V pattern, but these hydrogens, I'm not going to be using any dashed or wedged lines on them because they are all in that plane, because each one of these is trigonal planar. So you'll be seeing them as nice and flat. If I turn this model kit sideways, you can see that where that double bond is, everything is nicely in the same plane for us. It isn't until we really get to this tetrahedral carbon that I have on the end that we're going to see those dashed and wedged hydrogens or other atoms, other carbon chains associated with it coming out at you and going back behind the screen of the board. But you'll notice that we still have that same V pattern. If I were to look at my skeletal structure and continue my chain out even longer, you'll still notice that we still have that same type of V zigzag type pattern, and I'm never going to draw anything inside any of those V's. If I want to look at drawing other hydrogens, other carbons on there, they would be going outside of the V, not within the V itself. And once again, this really goes back to that trigonal planar shape that we have at those carbon atoms. The next one is going to be our alkyne. So remember that our alkyne is going to be our triple bonded carbon atoms. So when we actually look at our triple bonded carbon atoms, they're actually going to be a straight line pattern that we're going to see with our structures. There is no longer a V, there's no longer a zigzag, they are nice and linear. So if you look at our carbon atoms, they are linear. Here's carbon atom 1, here's carbon atom 2 on my model kit, which means that each one of those carbons only has 2 electron domains. So it is a very linear structure for us. And you want to make sure that you are drawing it linear. So if I were to look at this in terms of our Lewis structure, this is what my model would look like if I had those same 3 carbon atoms. I could put a carbon atom out there as well. This initial part is nice and linear. When I get to that tetrahedral carbon, then I start to see the zigzag again, or I would start to see the shapes. If I were to extend this structure into a very long structure in my skeletal format, this is what it would look like. The key is you want to make sure that those triple bonds are linear. They do not follow that same zigzag pattern that we were seeing earlier. So what you want to be very careful not to draw when we're drawing linear structures is a structure that looks like this. It doesn't have that same linear molecular shape that what that triple bond carbon needs to have. So this is what you want to try to avoid. If you see that on your paper, you've ended up drawing it, erase it very quickly and get back into that linear structure for those carbons that have the triple bond associated with them. So along with all this information, I do want to talk a little bit more about molecular dipoles. So we did look at dipole moments or dipoles within a single bond, but now we want to define those molecular dipoles in an entire molecule since we're going to be looking at these very large molecules. So the molecular dipole is going to define the polarity of an entire molecule, not just looking at any individual bond. We're going to determine those molecular dipoles based off of all the bond dipoles within the molecule. So you do need to be able to identify if a bond is polar or nonpolar based on those electronegativities. And we're also going to be looking for lone pair of electrons within our molecule as well to help us predict molecular dipoles. Molecular dipoles are going to define based on a dipole moment. The symbol for a dipole moment is that mu, lowercase mu, and it really defines the magnitude of that charge distribution at either end of the molecule, and it's going to be relative to the size of our molecule. So our formula for mu is that mu is equal to Q. Q represents the charge distribution, and then R, and R represents the distance, the size of our molecule from one end of this molecule to the other. Dipole moments are typically measured in Dubais, which is abbreviated with a capital D. 1 Dubai is going to be equal to 3.336 coulombs per meter. And remember, coulombs is our electrical charge unit, which then implies that we're going to be measuring those distances in meters. So we are going to be looking at dipole moments. I'm not going to make you calculate any dipole moments. We can define trends based on those dipole moments, and I'm really more concerned that you can get to the trend, predict if a molecule is polar or nonpolar, what molecules are more polar or less polar, really based on electronegativity differences and size of molecule differences. So I'm not going to make you do any calculations. This is here to kind of help you understand the trends that we will be looking at. Since we're going to be looking at trends, there are two things that you want to look for to determine if a molecule is polar or nonpolar. The first thing we're going to be looking for are polar bonds. A molecule must contain some polar bonds in order to be a polar molecule. If all the bonds within the structure are nonpolar, we have a nonpolar molecule. Most bonds are going to be polar in organic chemistry. When we have things like oxygens, nitrogens, highly electronegative atoms, we'll definitely have some polar bonds. If our molecule just contains bonds between carbon and hydrogen, those bonds are nonpolar for us. So if it just contains carbons and hydrogens, it's going to be more of a nonpolar molecule. That dipole moment will be very, very small. The other thing that we're going to be looking at is going to be the symmetry of the molecule. If we have symmetry within our molecule, all of those dipole moments, those bond dipoles, cancel out, and we have a nonpolar molecule overall if it is symmetric and it contains polar bonds. If it is asymmetric and contains those polar bonds, it's going to be a polar molecule because all those bond dipoles will not cancel out and will have some polarity associated with it. So the key is looking for the symmetry of the molecule as well. Anything that is symmetric will typically be nonpolar. Anything that has asymmetry due to different atoms or due to lone pairs is going to typically be a polar molecule. I also want to talk a little bit about an effect that we're going to see within an entire molecule. Because our molecules are so large, there's other ways that we can see some polarity differences within our molecule. And one of them is going to be the inductive effect. And this is the shifting of the electrons in a bond in response to electronegativity of atoms that are nearby. So these are not because of the atoms within the bond itself. It's because of neighboring atoms that are influencing the electron density areas that we're going to be looking at within the entire molecule. The inductive effect is going to play a very large role in reactivity. So we want to be able to define the inductive effect and look for the inductive effect within molecules because it will help us predict reactivity as we continue on this semester. What we're going to see is that metals inductively donate electron density. Remember, metals are very low in terms of their electronegativity, so they tend to inductively donate electron density when they are found in a molecule, meaning they'll push electron density onto other atoms. Non-metals, especially things like fluorine and oxygen and nitrogen, things that are highly electronegative, they will inductively withdraw electron density, meaning they're going to pull electron density from other atoms because of their electronegativity. So I do want to look at a couple of examples with molecular polarity and talk a little bit more about the inductive effect as well. So one of the examples that we're going to look at is carbon and bound to 4 fluorine atoms. So there's our nice tetrahedral shape. Remember, fluorine is one of our most electronegative atoms. It is the most electronegative atom on our periodic table. So it is going to pull all of its electron density from carbon to our fluorine. So each one of those bonds is highly polar. But you'll notice that this is a very symmetric molecule. So if we look at it as tetrahedral, all those atoms are the same. It's a very symmetric molecule. So overall, this is a non-polar molecule because of the symmetry. It contains very polar bonds, but it is a non-polar molecule. If we would compare this to carbon that is attached to 2 fluorines, and two hydrogens, the bonds between carbon and fluorine are very, very polar, pointing towards the fluorine, but the bonds between carbon and hydrogen are nonpolar for us. So now we still have polar bonds, but we have also lost the symmetry. If you think about this, here's what our molecule looks like, where we've got fluorines on one side that are pulling a lot of electron density over here. We've got hydrogens on this side. So this has a dipole moment. It does have polarity associated with it. This would be classified as a polar molecule because it has asymmetry now associated with it. What the inductive effect is telling us with this structure is that not only is the fluorine pulling the electron density away from the carbon, it's also starting to pull some electron density away from those hydrogens as well. So these hydrogens are actually partially positive because of the inductive effect. So you kind of think about it that fluorine is not just impacting the bond between carbon and fluorine, but it is also impacting the bond between the carbon and the hydrogen, and it's pulling all the electron density towards the fluorine atoms. That is our inductive effect, that highly electronegative atoms impact more than just their bond. They'll impact neighboring bonds as well. As we get farther and farther away, so if I were to extend this chain, it's not going to impact atoms that are way over here. They need to be close in proximity. So it's kind of those neighboring or nearby atoms that are going to be impacted by the inductive effect.